Okay, so now I'm going to talk about Biot-Savart's law. Biot-Savart's law is equivalent to Coulomb's law. Now, Coulomb's law in electrostatic is used when we want to find the force between two charges and when we want to find an electric field at a specific point caused by the charges near to it. Now, Biot-Savart is the same thing but for magnetic field. So basically, if I have a conductor carrying current here and the current is flowing in that direction, it's going to generate a magnetic field around it. So the direction of the magnetic field can be determined by using the right hand rule. So if you bring your right hand and you put your thumb into the direction of the current, the other four fingers will point to the direction of the magnetic field around the conductor. So as you can see, again, this is a three-dimensional figure drawn here on a two-dimensional surface. So to visualize the magnetic field or magnetic flux, you need to imagine the flux coming out from the page on top of the conductor, going into the page at the bottom of the conductor. Okay, so when you have a circle and a dot in the middle, that implies that the direction is going out of the page. And when you have a circle with a cross in the middle, like a Phillips screw head, then the direction is into the page. So basically, we use Biot-Savart to find the magnetic field strength at a specific point. So let's say we want to find what is the magnetic field at point P here caused by the current that is flowing here. So we can apply Biot-Savart to solve that problem. So the equation is given as the differential of magnetic field intensity is equals to I divided by 4 pi dl cross r divided by r squared, where r is the distance here. Okay, so when we apply integral to both sides of the equation, so h dh here becomes h, I over 4 pi is a constant, so we integrate over dl cross r divided by r squared. So the unit is ampere per meter, and let's look at an example on how to use this equation. So suppose you have a conductor shown in this figure here, and it has a length of L. And we want to find what is the magnetic field intensity, H, and magnetic flux density, B, at this point here, point P. So the current is moving upwards. So if you apply the right hand rule, so on the left hand side, the magnetic field will be coming out of the page, and on the right hand side, the magnetic field will go into the page. That's why we have an X here, because it's on the right hand side. If you were to find for the left hand side, then it's going to be a circle with a dot in the middle. All right, I hope you are well versed in the right hand rule by now. So if the direction of the current is reversed, then the direction of the magnetic field is also reversed. Okay, so this point P has a distance of r from the conductor, and we want to find what is the differential length first. Okay, differential length of conductor, and then we want to integrate for the whole length L. So what we do now is we apply the equation. So we have I over 4 pi as a constant, and we need to integrate because we already separate the line into two equal parts. So we need to integrate from negative L over 2 to positive L over 2. Right? And dl cross r, when we apply the cross product, dl cross r. L is in the direction of z, and r is in the direction of the radius. So z cross r we will get sine theta dz in the direction of phi. Okay, so phi is the circular angle. You need to refer to the Cartesian coordinate, Cartesian transformation to understand what the direction of phi means. Okay, it's on the xy axis, and the direction of phi is moving from the x-axis to the y-axis in that direction. Right. So you have this equation here. So you have sine theta over r squared dz. Now for convenience, we want to convert the variable z all into theta. So by using transformation, you'll get these three equations here, 5.26a to 5.26c. But how do you derive? So let me show you one by one. First, let's look at r, capital R equals to small r cosecant theta. How is this derived? Using this part here. We know sine theta is equals to r over capital R. So sine theta is opposite divided by hypotenuse. So opposite is small r divided by hypotenuse. Hypotenuse is magnitude of here, capital R here. So we rearrange, we get r equals to small r divided by sine theta. And since 1 over sine theta equals to cosecant theta, so we get capital R equals to small r cosecant theta. So this is how we derive for the first part. Now for the second part, we know that tangent theta is equals to opposite divided by adjacent. So opposite is R, adjacent is, in this case, Z. So we have Z equals to R over tangent theta. And tangent theta, 1 over tangent theta is cotangent theta. So we get Z equals to R cotangent theta. Since Z derived here in this context is a negative value, because Z here is located in a negative position in the axis, so we get Z equals to negative R cotangent theta. And finally, for the third part, is simply the differential of Z. So if you have dz over d theta, so then we have d over d theta negative R cotangent theta. So you need to know how to derive the differential equation. So you get it's equivalent to actually negative cosecant theta squared. So the negative cancel out. So you get dz equals to r cosecant squared theta d theta. Now remember, what we want to do is we want to calculate h and b. Now we've already do the transformation. We replace the respective values into the equation that we have gotten earlier. So we have, if we go back, we have sine theta dz divided by r squared. So these are the value. Dz is equal to r cosecant theta squared d theta, r squared. The magnitude of r capital R squared is r squared cosecant theta squared. So now it's convenient because we can cancel here cosecant squared theta and cosecant squared theta is cancelled, and r divided by r squared, so we get 1 over r. So because we want to integrate only over theta, so r below here becomes a constant, so we can take it out. We get I over 4 pi r between angles theta 1 and theta 2. Sine theta d theta. So when we convert this integral, we get in this form. It's cos theta 1 minus cos theta 2, where if you refer to this figure here, theta 1 refers to the inner angle from the starting point, and theta 2 refers to the outer angle from the end point of the conductor with the length L. Right? So we know cos theta is equal to cos is adjacent divided by hypotenuse, right? So theta adjacent, the length is L over 2. because we are only considering half. And hypotenuse R is R squared plus L over 2 squared square root. So we get the hypotenuse here. Okay, for cos theta 2, it's actually the inverse or negative of cos theta 1. So it's just applying negative here. It's the principle of trigonometry. And you get the angle theta 2 because it's the outer angle. If you were to calculate the inner angle, then by right, since this is a equal triangle because the length is the same, so theta 1 and theta 2 should be the same. The inner theta here. But because we want to know the outer, so we just apply negative. Right. So we already know that V equals to mu H. And if we assume mu R equals to 1, then we get B equals to mu naught H. We replace in this equation here. Right. And because if we want to consider an infinitely long line, if L is very, very long compared to the distance R, then we can assume R here is negligible. So if R is negligible, then we can assume it's only square root of L squared. So square root of L squared becomes L. We can cancel L from the bottom here with L on the top. So you get mu naught I over 2 pi R. So this is the relationship for an infinitely long wire, and this is the relationship if it's not infinitely long. So another way to put it is like this. For a semi-infinite conductor, okay, special case, semi-infinite conductor, that means we assume that the starting point is origin, but then it extends to infinity. So theta 1 will start at 90, while theta 2 will go up until 180. Okay, I hope you can try to imagine this. So let's say we have a semi-infinite line. So it starts at origin and it extends until infinity. So it starts at origin, extends until infinity. So when it starts here at point P, the angle theta 1 will be 90 degrees. And the angle theta 2, the outside angle, because it's very long, far away, approaching infinity, then theta 2 is going to be almost 180, or we can assume 180. So when we apply, we get I over 4 pi R in the direction of FE. Another special case is we have an infinite conductor that starts from negative infinity to positive infinity. So in that case, we have theta 1 equals to 0, the internal angle is 0, and the outer angle is the same, 180. So we have 1 minus minus 1. Previously, we have 0 minus minus 1. Now we have 1 minus minus 1, so we get 2 here. 2 and 4 can be cancelled, so we get H equals to I over 2 pi R in the direction of FE. Right? And when we apply B equals to mu H, and mu, we should know that it's actually mu naught multiplied by mu R. In most cases, mu R is equals to 1, so we can assume B equals to mu naught H. And by applying again, we get the same answer as previously. Here we get B equals to mu naught I divided by 2 pi R in the direction of phi. If I go back, it's also the same here. Two methods of derivation, we still get the same result. Well, actually not two different methods, but two different variations of derivation methods. Okay, so another important thing is the direction of the unit vector. So we need to see an example to understand this better. But anyway, to find the direction, it is equivalent to AL cross AR, where AL is the unit vector along the line of current, and AR, so this is a typo, is equal to unit vector perpendicular to the line of current. Okay, so Next is an exercise. So we have a conducting triangular loop that has 3 segments, 1, 2, and 3. So the current is 10 amps, 10 amps here. We want to find what is the magnetic field intensity at 005 caused by segment 1. Alright, so please refer to the video on how to solve this example.